Imagine standing in a pitch-black hallway late at night. Every instinct in your body is screaming at you to run, to sprint toward the safety of your bedroom, lock the door, and pull the blankets over your head. You hear a sharp, metallic click right behind your ear. Your heart slams against your ribs like a trapped bird. Blood surges into your thighs. Your lungs expand to pull in a sudden wave of oxygen, and your adrenaline levels spike to lethal thresholds. You are completely wired for action. Every cell in your motor cortex is screaming a single command: move. And yet, you can't. Your boots feel like they've been poured into solid concrete. Your arms hang like dead weights at your sides. You try to open your mouth to scream, but your vocal cords are clamped shut by an invisible pair of vice grips. You are entirely conscious, vividly aware of the threat looming inches away, yet your muscular system has been completely taken offline. You haven't chosen to stand still. Your free will has been revoked, bypassed by a primordial safety override that was coded into your central nervous system hundreds of millions of years before humans ever learned how to speak. For decades, popular culture and basic biology textbooks have repeated a simple three-word mantra when describing how living organisms respond to danger: fight or flight. We are told that when faced with a predator or a life-threatening crisis, the human brain performs a rapid calculation. It either prepares us to turn and strike back, or it fuels our muscles to escape at maximum speed. But anyone who is ever frozen in front of an oncoming vehicle, paralyzed by blinding headlights, knows that this two-option framework is fundamentally incomplete. There is a third, far more potent response that dominates the human threat hierarchy, one that doesn't involve moving an inch. Why does the brain, in the exact moment when speed and action mean the difference between life and death, pull its own emergency brake? Why would millions of years of natural selection preserve a mechanism that leaves an animal completely defenseless, pinned in place right in front of the mouth of a predator? To understand why your body betrays your willpower when terror strikes, we have to pull back the curtain on the deepest, oldest layers of the human brain, where logic gives way to raw neural circuitry and where fear transforms from an emotion into a physical cage. To decode the physics of paralyzed terror, we first have to strip away the illusion that our conscious mind is running the show. When you encounter a sudden threat, your logical brain, the prefrontal cortex sitting right behind your forehead, is entirely too slow to save you. Processing visual or auditory information through the conscious areas of the brain takes roughly 200 milliseconds. In an evolutionary environment where a saber-toothed cat or a striking viper can close a lethal distance in less than 50 milliseconds, waiting for your conscious mind to analyze the situation and decide whether to run or fight is an absolute death sentence. Nature solved this latency problem by creating a rapid response shortcut, a subconscious alarm center known as the amygdala. Tucked deep within the temporal lobes, this almond-shaped cluster of nuclei acts as an ultimate threat detection system. When sensory data enters your brain, whether it's the shadow of an intruder, a sudden loud bang, or a rustle in the tall grass, it travels directly to a relay station called the thalamus. The thalamus immediately splits the incoming signal into two distinct pathways. The first path is the slow road. It sends detailed, high-resolution data up to the visual and auditory cortex for deep analysis, allowing you to ask, is that a coiled garden hose or a venomous snake? But simultaneously, the thalamus sends a low-resolution, hyper-fast signal straight down the fast road to the amygdala. This path bypasses conscious thought entirely. Long before your eyes have fully processed the shape in the dark, your amygdala has already declared a red alert. Once triggered, the amygdala fires off electrical impulses down to the brainstem and the hypothalamus, unleashing a chemical cascade that floods your bloodstream with stress hormones like cortisol, adrenaline, and noradrenaline. Your heart rate skyrockets, your pupils dilate to let in maximum light, and your liver floods your blood with glucose to supply instant energy to your muscles. This is the classical sympathetic nervous system activation, the engine of fight or flight. However, the sympathetic response is only half the circuit. While your physiological engine is revving at maximum RPMs, another ancient neural circuit is simultaneously stomping on the brakes. This is where the classic freeze response begins, and it represents a brilliant, highly calculated evolutionary strategy that has kept species alive for hundreds of millions of years. Scientists who study animal behavior and human neurobiology divide the response to danger into a predictable, step-by-step progression known as the defense cascade. The freeze response is not a random glitch or a failure of nerve. It is a precisely timed phase within this cascade. The first phase is called attentional freeze or hypervigilance. Imagine a deer grazing in an open meadow. Suddenly, a twig snaps in the nearby tree line. Before the deer can decide whether to run or attack, it instantly freezes. Its body goes rigid, its ears swivel toward the noise, and its eyes widen. During this phase, heart rate actually drops dramatically, a phenomenon known as fear bradycardia. Why drop the heart rate when danger is near? Because movement creates noise and draws visual attention. Most mammalian predators, from big cats to wolves, are hardwired to detect motion. Their visual systems are tuned specifically to track moving prey against a static background. If an animal remains motionless, it effectively renders itself invisible in plain sight. Furthermore, freezing eliminates the noise of the prey's own footsteps and breathing, allowing its auditory system to gather maximum intelligence on where the predator is located and which direction it is moving. In this initial phase, the freeze is active and alert. It is not paralysis, it is a temporary hold button. Your muscles are primed and brimming with tension, holding massive amounts of kinetic energy, ready to discharge into an explosive sprint or violent strike the moment the predator turns its head or takes a step in the wrong direction. The brain is effectively keeping its motor idling while it gathers crucial environmental data. If the threat remains distant or uncertain, this freeze can buy precious seconds, allowing the predator to pass by without ever noticing its target. But what happens when the threat moves closer? What happens when the predator steps out of the shadow, looks you directly in the eye, and closes the distance? This is where the defense cascade shifts into its most extreme, terrifying territory, a state where the hold button transforms into complete physical lockup. When a threat becomes unavoidable, imminent, and physically overwhelming, when running is mathematically impossible and fighting back offers zero chance of survival, the nervous system abandons the active freeze and engages its nuclear option, tonic immobility. Tonic immobility is a state of profound, involuntary physical paralysis coupled with muscle rigidity or total flaccidity. While a person or animal in this state remains mentally conscious and painfully aware of everything happening around them, they lose all voluntary control over their skeletal muscles. Their eyes may remain open, fixed in an unblinking stare, but they cannot speak, turn their head, or move a single digit. To understand why this happens, we have to look at the dual architecture of the autonomic nervous system. The autonomic system is divided into two main branches, the sympathetic system, which drives action, and the parasympathetic system, which drives rest, digestion, and conservation. Normally, these two systems act like an accelerator and a brake on a car. When you step on the gas, you release the brake. When you apply the brake, you take your foot off the gas. During tonic immobility, however, the nervous system does something extraordinary and paradoxical. It slams both the accelerator and the brake down to the floorboard at the exact same time. The amygdala sends massive activation signals to the sympathetic nervous system, driving adrenaline levels to absolute maximums. But simultaneously, extreme life threat signals trigger a massive activation of the parasympathetic nervous system via a deep, unmyelinated branch of the vagus nerve known as the dorsal vagal complex. The dorsal vagal nerve is an ancient neural pathway inherited from early reptiles and amphibians. When activated, it induces an immediate freeze and flop shutdown. It dramatically drops blood pressure, slows the heart rate, lowers body temperature, and blocks the transmission of motor signals from the motor cortex down through the spinal cord. The result is a total physiological stalemate. Your internal engine is running at a redline rate of tens of thousands of revs, but the transmission has been completely disconnected from the wheels. You are trapped inside a body that has gone completely dead. From an evolutionary standpoint, why would nature build such a horrifying state of involuntary paralysis into our nervous system? The answer lies in the grim logic of predator dynamics. First, many predators lose interest in prey that appears to be dead. Big cats, bears, and wolves often prefer live prey, partly because dead meat in the wild carries a high risk of decay and lethal bacterial contamination, and partly because a motionless target fails to trigger their predator kill drive. If a prey animal goes limp, a predator may relax its grip, drop the prey on the ground, or look away for a brief moment to check its surroundings. That single moment of relaxed vigilance offers the paralyzed animal a narrow, miraculous window to snap out of tonic immobility and make a desperate escape. Second, tonic immobility triggers a massive release of endogenous opioids, the brain's natural painkillers. Endorphins and enkephalins flood the central nervous system, creating a profound state of analgesia. Physical pain is dramatically suppressed, and emotional horror is muted into a state of psychological dissociation. If an animal is about to be torn apart and consumed, tonic immobility acts as a biological anesthetic, shielding the organism from severe agony during its final moments. Finally, staying completely still during an attack minimizes physical damage. Thrashing around, screaming, and violently resisting while trapped under the claws or jaws of a larger predator often causes deeper tissue tearing, broken bones, and accelerated blood loss. By remaining rigid or limp, the prey reduces internal hemorrhaging and avoids triggering further aggression from the attacker. While tonic immobility served our mammalian ancestors well in the wild, its persistence in modern humans presents a deep biological tragedy. Because our neural circuits cannot distinguish between a prehistoric predator, a modern physical assault, a high-speed car crash, or a sudden terrifying event, the dorsal vagus nerve responds with the exact same primitive blueprint. In clinical studies of extreme trauma, such as physical violence, sexual assault, or combat, researchers have found that tonic immobility occurs in a massive percentage of victims, ranging from 30 to over 50%. During a violent encounter, a victim's brain may instantly assess that escape is impossible, and resistance will lead to immediate death. Within milliseconds, the dorsal vagus nerve fires, locking the body in place. Tragically, because most people are only taught about fight or flight, victims who experience tonic immobility often suffer from overwhelming guilt and self-blame after the event. They ask themselves, "Why didn't I scream? Why didn't I push them away? Why did I just stand there?" Science offers a clear, undeniable answer. It was not a choice. It was a reflex. Volitional control was completely stripped away by subcortical brain structures that operate entirely outside of conscious awareness. Blaming someone for freezing during a life-threatening trauma is like blaming someone for blinking when a gust of wind hits their eye, or blaming their knee for jerking when struck by a doctor's hammer. The decision was made by an ancient survival algorithm long before the logical mind could even process the reality of what was taking place. This same mechanism explains the phenomenon of sleep paralysis, a bizarre, terrifying state where the mechanics of fear and immobility collide in the bedroom. During REM sleep, the phase of sleep where we experience our most vivid dreams, the brainstem intentionally paralyzes our body through a process called REM atonia. Neurons in the brainstem release inhibitory neurotransmitters like glycine and GABA, blocking motor signals to prevent us from physically acting out our dreams and injuring ourselves in our sleep. Occasionally, a glitch occurs in the sleep architecture. Your conscious mind wakes up, but the brainstem fails to turn off REM atonia. You open your eyes, look around your bedroom, and discover that you cannot move a single muscle except for your eyes and diaphragm. Finding yourself suddenly paralyzed in the dark immediately triggers the amygdala. Sensing an extreme threat, the brain panics and starts manufacturing explanations for why you are immobilized. It projects terrifying hallucinations onto the environment, the infamous shadow man standing in the corner, or a heavy demon sitting directly on your chest. Your heart races, adrenaline pours into your veins, and you try to scream for help, but the motor blockade remains locked. You are experiencing a synthetic version of tonic immobility, a state where waking consciousness, deep-seated neuroparalysis, and primordial fear fuse into a single horrific waking nightmare. To fully grasp why the brain's motor signals get choked off during intense fear, we must examine the specific neural hardware involved in translating thought into physical action. Voluntary movement originates in the primary motor cortex, a strip of neural tissue running across the top of your head like a headphone band. When you decide to move your arm, electrical impulses fire from the motor cortex, travel down through the internal capsule, pass down the spinal cord, and exit through peripheral nerves to contract your muscles. However, the motor cortex does not act alone. It is constantly modulated by deep brain structures known as the basal ganglia and the cerebellum, which regulate movement fluidly. Surrounding these systems is the limbic system, the emotional core of the brain. When fear spikes to extreme levels, the amygdala sends massive inhibitory outputs directly to a region in the brainstem called the Periaqueductal Gray, or PAG. The PAG is the central control hub for defensive behavior in all vertebrates. It is anatomically divided into different subregions, each responsible for a distinct survival strategy. When a threat is detected at a distance, the lateral and dorsolateral regions of the PAG are activated. These regions trigger the active freeze and fight-or-flight responses. They increase blood pressure, enhance muscle tone, and prepare the motor cortex for explosive physical activity. However, when a threat becomes immediate, unmanageable, or physically overwhelming, the electrical activity shifts dramatically to the ventrolateral region of the PAG. The VLPAG acts as the ultimate circuit breaker. It sends powerful inhibitory signals down the reticulospinal tract in the spinal cord, directly blunting the alpha motor neurons that control your skeletal muscles. At the same time, the flood of stress hormones causes severe functional disruption in the prefrontal cortex, the seat of executive decision-making and motor planning. Under high-stress conditions, excess levels of noradrenaline and dopamine completely shut down the firing of prefrontal networks. This phenomenon, known as stress-induced prefrontal shutdown, effectively severs communication between your conscious intentions and your motor hardware. Your logical mind may be screaming, "Move, run, fight back," but the message never leaves the brainstem. The wire has been cut at the level of the PAG and the spinal cord. The physical body is no longer taking orders from the captain on the bridge. It has been placed under automatic lockdown by the emergency systems in the engine room. Understanding that fear-induced paralysis is a hardwired biological response raises a critical question. Can we overcome it? Is it possible to bypass the biological emergency brake when terror strikes? Or are we permanently at the mercy of our ancient brainstem? The answer lies in understanding how professional operators, such as military special forces, firefighters, emergency room surgeons, and martial artists, train to operate under extreme life-or-death pressure. When an untrained individual encounters a sudden life-threatening crisis, the novelty and intensity of the threat trigger an immediate flood of raw amygdala activation, cascading straight into prefrontal shutdown and potential tonic immobility. The brain has no pre-existing software script for the situation, so it defaults to its most primitive hardware response: freeze. To prevent this neural overload, tactical training relies on a process called stress inoculation and procedural automation. By repeatedly exposing individuals to realistic, high-stress scenarios in a controlled environment, trainers force the brain to build preformed motor neural pathways, often referred to as muscle memory. When an action is rehearsed thousands of times, the neural instructions migrate out of the slow, conscious prefrontal cortex and become hard-coded into the basal ganglia and cerebellum. When a trained individual encounters a crisis, their brain does not need to analyze the situation from scratch or search for a response. The instant sensory input triggers the automated motor script stored in the basal ganglia, bypassing the slow prefrontal cortex and overriding the inhibitory signals of the ventrolateral PAG. The motor action executes automatically before the amygdala can pull the emergency brake. Another powerful technique for breaking the freeze lock involves intentional autonomic regulation through breathing. Because the freeze response is driven by the dorsal vagal complex and an unmanaged sympathetic spike, conscious control over the respiratory system offers a direct backdoor into the autonomic nervous system. Techniques like box breathing, inhaling for 4 seconds, holding for 4 seconds, exhaling for 4 seconds, and holding empty for 4 seconds, activate the ventral vagal complex, the newer myelinated branch of the vagus nerve that promotes calm, social engagement, and conscious control. By manually controlling your respiratory rate, you send physical feedback signals back up through the vagus nerve to the brainstem, signaling that oxygen levels are stable and the immediate biological collapse is unnecessary. This lowers the heart rate, reduces the inhibitory output of the PAG, and restores communication to the motor cortex, allowing voluntary control to return to the limbs. Ultimately, the ability to freeze when terrified is not a flaw in human engineering. It is a profound, deeply ancient mechanism forged in the fires of millions of years of mammalian survival. It is a testament to the complex, layered history of the human brain, a masterwork of evolutionary architecture that prioritizes keeping you alive above all else, even if it has to lock you inside your own body to do it. The next time you find yourself frozen in place by a sudden fright, remember that you are not failing. Your brain is executing a code that was written in the shadows of prehistory, an ancient biological shield designed to make you invisible, protect you from pain, and keep you alive for one more day in a world full of unseen dangers.